Okay, let's unpack this. When we say we're diving into algebra today, you might be thinking, oh no, high school math flashbacks.
Yeah, right. But we're looking at it through the lens of the foundational physics lectures.
Exactly. And here, algebra isn't just, solving for x. It's about seeing this incredible, elegant structure that holds up, well, everything in physics.
Yeah. Our source material today, it's less about the doing of algebra and more about appreciating the architecture of it all.
That's a good way to put it, architecture.
Feynman talks about the enjoyment you get from seeing the grand design. So our mission today really is to trace how these super basic rules, the ones you get from just counting things,
Like apples and oranges.
pretty much how those rules were generalized, pushed step by step, until they basically forced mathematicians to invent this whole system we call elementary algebra.
So it's about the why. Why are the rules the way they are, not just memorizing them?
Exactly. The why.
Okay, so let's start right at the beginning. The ground floor. Positive integers, just numbers you count with.
Yep, that's where the initial assumptions come from. The axioms everything else has to follow.
Like the commutative laws.
Right. Order doesn't matter for adding or multiplying. So a plus b is b plus a, and a times b is b times a. Simple enough.
Seems obvious almost.
It does when you're thinking about counting objects. Then you've got the associative laws. That's about grouping.
So if you're adding three things, say A, B, and C, it doesn't matter if you add A plus B first, then C, or if you added 2, B plus C. You get the same answer.
Precisely. And the one that links addition and multiplication?
Ah, the distributive law. That's A, B plus C equals AB plus AC.
You got it. That one's key. Plus, you need the special rules of 0 and 1. Adding 0 does nothing. Multiplying by 1 does nothing. Identity elements.
It really is amazing that this whole complex world starts from just those few ideas, based on counting.
It is. But the system doesn't really start to grow until you think about undoing things.
Inverse operations.
That's the engine driving it. Algebra defines new operations as the inverse of the old ones. You have addition. Well, how do you solve a plus x equals b?
That gives you subtraction.
Right. And if you have multiplication, x equals b.
The inverse is division.
Exactly. And it keeps going. Powers. They have two inverses depending on what you're solving for.
Oh, right, like finding the root if you know the power, or the logarithm if you know the base and the result.
Solving x to the power b equals c gives you the root. Solving b to the power x equals c gives you the logarithm. This constant need to reverse things is fundamental.
And that need, that insistence on having an inverse, immediately pushes us beyond those simple positive counting numbers.
Immediately. Think about it. You've got your nice rules for positive integers. Now try to solve, say, 3 plus x equals 2.
Right. If you stick to the rules of arithmetic, x has to be minus 1.
There's no other consistent answer. So 0 and negative numbers weren't just pulled out of thin air.
They were a logical consequence of making the rules for subtraction work everywhere. Even when it seems weird, like having negative apples.
Exactly. The internal logic of the algebra demanded them. The symbols had to be accepted to keep the structure consistent.
Okay, and the same logic applies to division.
Yep. Try solving 3 times a equals 5 using only integers.
You can't.
You can't. So you're forced to invent the fraction 5/3. Rational numbers, they come directly from generalizing division.
So the pattern is establish rules for the simple case, then demand those same rules work, even when you try to invert operations or solve new problems.
That's the core idea of abstraction here, and it goes even further into powers. If you insist that the rule a to the x times a to the y equals a to the x plus y.
The one where you add the exponents when multiplying.
Right. If you insist that rule must always work even if x or y are negative or fractions, well, that dictates what those things mean.
Okay, give an example, like a negative exponent.
Sure. Take a to the minus x. What could that mean? Well, if the rule holds, then a to the minus x times a to the x must equal a to the minus x plus x, which is a to the 0.
And anything to the power 0 is 1.
Right. So a to the minus x times a to the x must equal 1. The only way that works is if a to the minus x means 1 divided by a to the x.
So the rule defines the meaning, not the other way around. That's a really powerful shift in thinking.
It really is. That's the heart of mathematical abstraction. You expand what counts as a number by demanding the original laws stay consistent.
Okay, so we have integers, negatives, fractions. But then things got really tricky with an equation that looks super simple. X squared equals 2.
Ah, yes, the irrational hurdle. This was a genuine crisis point for the ancient Greeks, the Pythagoreans.
They couldn't find a fraction, like p over q, that when you squared it gave you exactly 2.
They couldn't, and they proved it was impossible. This forced the acceptance of a whole new kind of number, irrationals.
Numbers like the square root of 2, or pi, things that have decimal expansions that go on forever without repeating.
Yep. You can't write them down perfectly as a fraction.
So now the number system includes these. Well, these very awkward numbers. Essential for geometry, like the diagonal of a square. But tricky. How did people actually work with them, especially with powers? Before calculators, raising something to the power of root 2 seems like a nightmare.
It does. And that practical need drove the development of tools. The big one was logarithms.
Ah, logs. Another high school terror for some.
Huh, maybe. But they were a computational miracle. Logarithms are basically the inverse of raising to a power, where you solve for the exponent.
And the key trick was,
The key rule. The log of a product, a times c, is the sum of the logs. Log a plus log c.
so it turns multiplication, which is hard, especially with messy numbers.
Into addition, which is much, much easier. You'd have tables of logarithms, look up log a, look up log c, add them, then look up the number corresponding to that sum. Boom, you've multiplied a and c.
Those tables must have been incredibly difficult to create accurately, dealing with all those irrational values.
Oh, the ingenuity was amazing. Take the method used by Briggs, who worked on base 10 logs. It's called the successive square roots method.
Okay, how did that work?
You start with your base, say 10, then you take its square root, then the square root of that, and again, maybe 10 times, 20 times. Feynman mentions 24 times.
So you're getting numbers like 10 to the power of 12, 14, 18, eventually 10 to the power of 1 over 2 to the 24. Really small exponents.
Exactly. Like 10 to the power 1 over 10 to the 24 is tiny, about 1.0022. You create a library of these values, these small fractional powers of 10.
Okay.
Then, the clever part. Any number you want to find the logarithm of can be constructed by multiplying together the right combination of these tiny power of 10 values.
Like building it up piece by piece.
Precisely. By multiplying these base numbers, you're adding their small fractional exponents, so you could compound them to figure out the total exponent that the logarithm needed to produce any target number with incredible precision.
Wow. That is clever. It's like they mapped out the irrational landscape using these carefully chosen stepping stones.
It's a beautiful demonstration of taming irrationality through methodical approximation. Of course, computers do it different, Val, but the logic was sound.
So we've gone from counting to negatives, fractions, irrationals, handling them with logs. But there was one more impossible problem waiting, wasn't there?
The final frontier for elementary algebra, yes. The equation x squared equals -1.
Right. Because any real number, positive or negative, when you square it, you get a positive result.
Always. So again, faced with an equation they couldn't solve using existing numbers, what did they do?
They didn't break the rules. They expanded the numbers.
Exactly. They had defined a solution. Let's just call it the square root of -1. I, the imaginary unit.
And suddenly we're off the number line. We need a new dimension.
We do.
Yeah.
And accepting I leads directly to the concept of a complex number, a number with two parts, a real part, R, and an imaginary part, Q, written as R plus IQ.
Like a coordinate on a plane instead of a point on a line.
You can think of it exactly like that, the complex plane.
Okay, but working with these,
Yeah.
how do you do arithmetic, especially division? It seems like you'd get i's stuck in the denominator.
And that leads to another essential tool, the complex conjugate. If you have a complex number, say x plus iw.
Its conjugate is x minus iw. You just flip the sign of the imaginary part.
Right. And why is this so useful? What happens when you multiply a complex number by its conjugate?
Let's see. X plus iy times x, you get x squared minus xe minus I squared y squared.
And since I squared is -1,
That last term becomes plus y squared. The xe terms cancel, so you just get x squared plus y squared.
which is always a positive real number, no i's left.
So to divide complex numbers, you multiply the top and bottom of the fraction by the conjugate of the denominator. That makes the denominator real, and then you can simplify.
Precisely, it's the standard trick. Again, a computational necessity born from maintaining consistency within this new number system.
So just like needing negatives or fractions, needing the conjugate is forced by the structure itself.
It really is. And this move into the complex plane, treating numbers as points, x, y, where the number is x plus iy, has absolutely profound consequences, especially when you extend the idea of powers to complex exponents.
Like raising 10 to the power of x plus I. What does that even mean?
It means algebra is suddenly deeply connected to geometry. That complex plane isn't just a calculating trick, it's where the unification happens.
And this is where we get to what Feynman calls the jewel.
The absolute jewel of mathematics, the result that ties so much together, Euler's formula.
Okay, lay it on us.
It states that e, the base of natural logarithms, raised to the power I times theta. So e to the I theta equals cosine theta plus I times sine theta.
Wow. Okay, break that down. E is about growth, I is the imaginary unit, and theta is an angle.
And cosine theta and sine theta are the geometric functions describing projections on the x and y axis for that angle theta in a unit circle.
So, an exponential function involving an imaginary number is directly equal to a position in the complex plane described by trigonometry.
Exactly. It shows that exponentiation, complex numbers, and trigonometry are not just separate topics. They are fundamentally interconnected. They naturally arise from consistently applying the basic rules of arithmetic we started with.
That's incredible. You start with 1 plus 1 and 2, and you end up unifying exponentials and trigonometry via imaginary numbers.
It's the ultimate payoff for that relentless generalization.
So looking back, the big takeaway for you, the listener, is what? We went from counting rules to negative numbers, fractions, irrationals, complex numbers.
All because we insisted that those original simple rules, like the commutative and distributive laws, had to keep working, even in these new, weird domains.
The system had to be internally consistent.
That's the key. Elementary algebra isn't just a random toolkit. It's this beautiful, integrated, logical structure. Every time math hit a wall, an equation it couldn't solve, like x squared equals 2 or x squared equals minus 1,
The response wasn't to change the rules, but to expand the definition of what a number could be.
right. And the success is undeniable. This process gave us tools like logarithms and complex numbers that are absolutely essential for describing the real world in physics, all built on those first few assumptions about counting.
It really leaves you thinking, doesn't it? That maybe mathematics isn't something we entirely invent.
But perhaps something we discover, like the structure was always there waiting for us to push the boundaries, ask the impossible questions like, what's the square root of minus 1? And reveal these incredibly deep connections, like Euler's formula, tying it all together, from counting apples to the foundations of wave mechanics. That's the power of abstraction.